Good morning. This is Professor David J. De Los Reyes. I've got a new topic this afternoon. It's Sunday afternoon here in Los Angeles. Okay. Let's proceed. My lesson for today is still differential equation. I am now on lesson DE08 on my course differential equation. And the title of this topic is differential equation, third order. Third order. Yesterday I discussed second order. Okay. Third order variable separable with the number 6 over here, meaning this will be my fifth example on the example problem on the evaluation of a variable separable. We are now through with first order. We are now through with second order. So this afternoon I will be discussing third order. Then maybe the next topic will be an application problems of a variable separable differential equation in real life. I will give you an example problem of a falling satellite coming from space. That's the next topic. Okay, let's proceed. The problem this afternoon is still a evaluation of a variable separable differential equation. My next lesson after this will be an example problem on the real problems, a falling satellite maybe. Okay, let's proceed. We are given y triple prime equal to 6. Triple prime. Triple prime. That's a single prime, that's double prime, and that's triple prime. So there are 4, that's fourth prime. If there are 5, fifth prime. So this is red prime. That is in integral calculus. Okay, I will erase this one so it will look good. The given initial conditions, we've got 3 initial conditions. Since this is y triple prime, meaning the order of the differential equation, the order is actually 3. What's the significance of the 3? Meaning y as a function of x, the required answer was differentiated 3 times. That's why this is y triple prime. Okay? So to bring out y as a function of x, we should have a combination of 3 initial conditions. The 3 initial conditions are these: x equal to 0 when y is equal to 2, dy dx is equal to 0 when x is equal to 0, and d square y over dx square. Oh, this is actually y double prime, and this is y prime. Okay, so don't be afraid of y double prime. Y prime is just dy dx, y double prime is just the second derivative of the first derivative. The third initial condition is d square y over dx square, or y double prime is equal to 0 when x is equal to 0. Okay? This is y prime. This is y double prime. Okay? For me, I prefer the term dy dx instead of y prime. And I prefer d square y over dx square instead of y double prime. But I know for a fact that y prime is dy dx and y double prime is d square y over dx square. Okay? Don't be tricked with the without knowing the relation of this one, you will be lost. So I'm telling you y prime is dy dx, y double prime is d square y over dx square. Okay, let's try to bring out the solution. The problem is asking for y as a function of x. Okay, and we are given 3 initial conditions. So supposed to be the required is actually the particular solution. Okay? Let's try to bring out the solution. Take it easy, guys. Easy money. If you are saturated with problems in differential calculus and integral calculus, that is on the differentiation and integration, there will be no problem on differential equation. Okay, let's proceed with the solution. I place it here. The derivative with respect to x of y is equal to y prime. And the derivative with respect to x of the first derivative is just actually, if we try to simplify this one, this can be written also as a d square y over dx squared, and that is actually y double prime. And the derivative with respect to x of d square y over dx squared is y triple prime. This is actually y double prime, and this is y prime. You got it, guys? Meaning the derivative with respect to x of y prime is just y double prime, and the derivative with respect to x of y double prime is y triple prime. Okay, that's the trick of the solution. So if we try to get this relation now, the third one, okay, d cube y over dx cube is equal to y prime, but d cube y over dx cube is actually the derivative with respect to x of the second derivative, and this should be equal to 6. Okay? Let's try to separate the variables. So we will multiply all terms by, sorry guys, my ink is almost gone. We multiply all terms by dx. Okay, I will use the red one. Left hand side, this cancels. What remains on the left will be the differential of the second derivative equal to 6 times dx. This is 6 dx. We separate the variables already. So we must have to proceed with the integration. So the integral of the differential of the second derivative equal to the integral of the right hand side, which is 6 dx. The integral of the differential of this one, from integral calculus, if the integral goes near the differential sign, they will try to cancel out each other. Okay? So what remains on the left will be d square y equal to, the integral of the right hand side is a constant times dx. We bring out the 6, then we integrate dx, and the integral of dx is just x plus k1. Okay, so actually we are given a general solution involving the second derivative. So we could proceed with the first derivative. We must have to compute for the value of k1. And to compute for the value of k1, we need the initial condition. From the problem, the second derivative is equal to 0 when x equal to 0. So I place it here, but d square y over dx squared is equal to 0 when x equal to 0. These are the initial conditions, 0 and 0. So substituting, 0 will be equal to 6 times 0 plus k1. Okay, therefore k1 will be 0. So we now know the value of k1. So actually we could now compute for the value of the second derivative, general solution. General solution of the second derivative. We go back here, therefore d square y over dx squared equal to 6x plus k1, but k1 is 0. So this is plus 0 or just simply 6x. This is now the particular solution for the second derivative. There are no more unknown constants, okay? Let's proceed. But what is a second derivative? Second derivative is the derivative of the first derivative. Therefore, we could rewrite this one as the derivative with respect to x of the first derivative, okay, and this equal to 6x. Then we multiply again both sides by dx, right? This dx cancels. What remains on the left will be the differential of the first derivative equal to 6x dx. Okay? We separate the variables already. Okay? The topic is variable separable, guys. Integrating both sides. The integral of the differential of the first derivative equal to the integral of the right hand side, which is 6x dx. The integral of the differential of the first derivative, this will cancel out. What will remain on the left will be dy dx equal to constant times a function. We bring it out. The integral of x dx, power formula, x squared over 2 plus k2. Therefore, dy dx equal to 3x squared plus k2. This is now the general solution for the first derivative. General, because we do not know the value of k2. Let's try to compute for the value of k2. We need another initial condition. From the condition in the problem, dy dx equal to 0 when x is equal to 0. So we need these two values here to compute for k2. 0 now will be equal to 3 times 0 squared plus k2. K2 will be 0. Okay? So we go back here, we place the computed value of k2, therefore dy dx is equal to 3x squared plus 0 or simply 3x squared. This is now the particular solution of the first derivative. Okay? And we are to solve for y as a function of x. So we got one more step before we could go to this. Okay, the derivative dy dx is actually can be written as the derivative with respect to x of 1. What we are looking for. Okay, equal to 3x squared. And again, multiplying both sides by dx, this dx cancels. What remains on the left will be the differential of y equal to 3x squared dx. We separate the variables already. Variable separable the topic, right? Integrating both sides, the integral of differential of y equal to the integral of 3x squared dx. The integral of the differential of y, this cancels out. So what remains on the left will be y equal to constant, a power function. So we bring out the 3. The integral of x squared dx will be, it is under the power formula, guys. It will be x cubed over 3 plus k3. Or actually, this cancels, or y is equal to x cubed plus k3. This is now the general solution for y. General solution. We do not know for the value of k3 for the meantime. But we are given the third condition over there. But y is equal to 2 when x equal to 0. Solving for k3, 2 will be equal to 0 cubed plus k3, or k3 will be equal to 2. So going back to the general solution, we will substitute the value of k3 to be equal to 2. Therefore, y is equal to x cubed plus 2. This is now the particular solution. And this is actually our answer. Okay? We are now given y as a function of x. Meaning our final answer will be y equal to x cubed plus 2. And how about the graph of this one? The graph of this one, it's still like this will be x, this will be y. Our answer is actually equal to x cubed plus 2. If you put x to be 0, y will be 2. At x equal to 0, y is 2. It is this. When x is 1, this will be 1 plus 2. When x is 1, y will be 3. When x is 2, it will be 8 plus 2, it will become 10. X equal to 3. 2, 3, 3. It will be here. So as you notice it, this will be the graph. And the equation of this is y equal to x cubed plus 2. You see it, guys, if I will try to put an arrow. What's the significance of that one? It seems it's just like the fat of a missile fired from a submarine or from a battleship. Missile pad. Okay, guys? Oh, so that's the solution of our problem. Y double prime equal to 6. The final answer will be equal to x cubed plus 2. And if we try to graph this, it seems it's just like a path of a missile fired from a submarine or from a battleship. Initially, okay, it will go up, then it will go where it was designed to strike. Good afternoon, Los Angeles.